What are sieves as Xenakis defines them? Sieves are algebraic structures used to generate outside time scales, like pitch, duration, intensity, etc. Most traditional music is based on repeating sequences of intervals. This repetition occurs primarily at the octave. In C major, the same sequence of intervals is repeated, starting at every octave of C. This sequence can be written, as Xenakis does in his book Formalized Music, as 2-2-1-2-2-2-1. This notation shows the semitone intervals between two successive notes in the scale, two semitones between C and D, and between D and E, one semitone between E and F, etc. Xenakis then presents the major scale in this form. Here, the indices represent the starting note of the set of 11 semitones contained in an octave. Thus, 12 indice 0 is a C that repeats at every octave, modulo 12, that is. He then takes the abstraction a step further by representing this same scale with the following formula based on minor and major thirds. You can check it out, it works. UPISketch offers a simplified approach to using sieves. We'll stick with the first representation, which allows for numerous possibilities. Thus, 1-2, an infinite repetition of intervals of one semitone and two semitones, will be Messiaen's mode 2. Note there's an option available when defining grids, which is the total range of this sequence of intervals. By default, when we enter 1-2, the range is calculated as the sum of the intervals, which is 3, and displayed in the corresponding field. However, we can specify a different range. For example, if we enter a whole tone scale, which will be defined by 2, the total will be obviously 2, but if we enter 4 instead, we get a major third scale. Note that the starting note is determined by the vertical position of the sieve on the page. Similarly, a whole tone scale can also be defined over an octave as 2-2-2-2-2-2, which is 6 times 2. In this case, the total is 12. If we change this range to 18, what happens is that we divide an octave plus an augmented fourth into 6 equal intervals. Each interval will be 3 semitones. You can verify this by referring to the background grid currently set to semitones. It is thus possible to create all sorts of particularly exotic and non-octavian modes, such as 1, 3.14, 4, 2.67, which would repeat over a range of 4.5 semitones. The definitions for sieves include a line for pitch as well as another line for time. They follow the same principle. In this case, the range, which was an absolute value in semitones, is replaced by the total duration, which is an absolute value in seconds. To reproduce the rhythm mentioned by Xenakis, simply enter 3-3-2. Since the default total duration for this rhythmic motif is 8 seconds, we can enter a different total duration of 4 instead, to more closely match the example, assuming a quarter note at 16. Once a sieve has been placed on the page, if you want to see its effects, you must apply a remagnetization to the gestures. This remagnetization can be performed based on several criteria. Based on several criteria: pitch, time, time and pitch, or onset dates of the sounds. Remagnetization doesn't apply to undefined parameters. For example, nothing will happen if you try to apply a sieve with an empty time definition using the time or time plus pitch mode. It is possible to organize mosaics of sieves with different definitions for each one. The gestures passing through this mosaic will be subject to local influences. Regarding the onset date, it's clear that the density of the gestures must roughly correspond to that of the time sieve. Here, for example, we generated a sequence using the automata tool with events placed every quarter of a second. The applied time grid is a simple triplet of quarter note plus an eighth note, which produces events twice per second. Since there were previously 4 gestures per second, the gestures will now aggregate in pairs at each grid point. The same grid in onset times mode applied to a set of gestures placed every 5 seconds would not have a noticeable effect. How to use mathematical expressions for sound synthesis. From the very beginning, UPISketch has used 2 concepts that are fairly common in computer music related to musical composition. Scores on the one hand and instruments on the other. In UPISketch 4.5, a new synthesis mode introduces the ability to create timbres from mathematical expressions. This offers a new type of tool, a new completely open set of instruments. The expressions take into account 3 types of temporal variables. X, which is the instantaneous phase between 0 and 2 pi, repeats at each period. T, which is the time in seconds since the start of the gesture, so it's 0 at the beginning. And U, which is the normalized time of the gesture between 0 and 1. 0 at the beginning, 1 at the end. X is the variable that defines what happens during one cycle of the oscillator. Writing sine of x is equivalent to creating a synthesizer that will produce a sine wave whose frequency is determined by the pitch curve of the drawn gesture. T will allow us to add transformations on a timescale larger than a single period of the sound. For example, a tremolo by multiplying sine of x by 0.5 plus 0.5 times sine of 2 pi times 5t. In this example, sine of 2 pi times 5t is a sine wave that oscillates between -1 and 1 at a stable frequency of 5 Hz, which doesn't depend on the frequency associated with x. Here is another example to illustrate the use of the variable u. An exponential envelope can be applied, which will modify the sound's amplitude if we multiply sine of x by e to the -5u. In this case, since u is normalized, it ranges over the interval 0, 1 over the total duration of the gesture. The envelope will therefore have a slower rate of decay when the gesture is longer. Whereas with sine of x times e to the -5t, the rate at which the amplitude decays will remain constant, regardless of the gesture's duration. Here is also an example of additive synthesis with integral ratios and with non-integral ratios, which will produce inharmonic spectrum. It goes without saying that, depending on the situation, the perceived pitch may be completely uncorrelated with the pitches drawn on the page. A wide range of mathematical functions is available. People who are intimidated by math can start with existing examples and modify them.